Let's talk the Coriolis effect. The Coriolis effect is a phenomenon that occurs in rotating non-inertial reference frames that affects the perception of an object's direction of travel. A common misconception about the Coriolis effect is that the effect is a force itself, but this is not the case, as it is actually the direct result of our rotation, the viewer, and not the object's. In addition, it's important to note that as the Coriolis effect only impacts the perception of the object, it doesn't actually affect the velocity of the object, assuming all other forces stay constant. Take it away, Thomas.
We start with understanding the equations behind relative position. Solely A or B refers to the fixed xyz axis, while the lowercase subscript xyz refers to the set of axes rotating with angular velocity omega. Next, we can take the derivative of both sides to yield the following. The final equation gives us the velocity of point B with respect to the fixed axes. Another differentiation leads to the acceleration of point B with respect to the fixed axes. Similar steps can be taken, such as product rule and substitution, to yield the final equation. The only difference between this equation for the rotating axes and that of translating axes is the Coriolis acceleration, signifying the difference in the acceleration of point B as measured from non-rotating and rotating xyz axes. If we represent the Earth as this merry-go-round, pretending the center is looking down at the North Pole and the outer circumference represents the equator, we can see this more clearly. As the merry-go-round is spinning, the ball is thrown inwards. While the ball does maintain a linear path, to the rotating outside observer it seems to have followed a curved trajectory towards the right. With non-rotating axes, the trajectory is straight, as expected. And we can also verify the linear path of the ball by using a marker against a ruler while the plate below rotates.
Previously, we discussed that the Coriolis effect gives off the illusion that objects traveling on a rotating reference frame appear to have some sort of curvature when in motion. If we think about it, what's one rotating reference frame that we're sitting on right now? That's right, planet Earth. Across a short distance, the Coriolis effect is pretty negligible. But what about over miles, or even continents? Say you're somewhere in Algeria, and you want to throw a ball straight northwards towards France. Even if you have the arm strength to do that, you might find the ball ends up curving towards Romania instead. Due to the eastward rotation of the Earth, a ball would end up curving slightly towards the east when you're aiming the ball straight, in reference to a fixed reference frame.
As can be seen, the Coriolis effect has numerous applications in the world. Thanks so much for watching this video, and we hope you enjoyed the following bloopers from when we originally attempted to film this video. Thank you.
That's right, planet Earth. Okay. Now, if we try to throw an object across a short distance, it appears to travel in a straight line.
Ow.
Even though...
Go. And go.
Let's...
Hard Gustav de Coriolis, who... Never mind, I'm done. I failed everything. Still recording, so...